Okay, we're beginning section 7.3, where we're going to learn to apply trigonometric functions to finding the trig functions of angles on the unit circle. Okay, so if you recall from the last section, we learned about coterminal and reference angles, and we're going to be using those to find sine, cosine, tangent, and also reciprocal functions of angles on the unit circle. Okay, so what we want to remember is on a unit circle, the radius of the circle is 1 unit. Okay, and what we're going to do is on this circle we see here, I'm going to go ahead and I'm going to draw a radius from the origin to a point on the circle, and that length will be 1 unit. Okay, and as you can see here, what we're going to do is we're going to make that radius the hypotenuse of a right triangle, where the hypotenuse has a length of 1 unit. Okay, so here's that radius, and what we're going to do is we're going to extend down and we're going to create one leg of a right triangle here, and we'll create another leg of that right triangle here. And right here, we'll label the angle that's formed between the terminal side of the angle and the positive x-axis, theta, as we've done before. Okay? Now, regarding the point here where the radius intersects the circle, we can label that point with a coordinate. Okay, so in general terms here, we know that if we start at the origin and we move a certain number of units to the right, we can say that we've moved x units. And furthermore, if I go upward from the point where I've stopped on the x-axis up to the point where the radius intersects the unit circle, I've gone up y units. Okay, and so now what I can do is I can label the coordinate on the unit circle. And what I'm going to do is, again, in general terms, I'm going to label that point x and y. Okay. Now, let's see how that relates to sine, cosine, and tangent. So we remember SOHCAHTOA, where sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so let's write each of these trig functions in terms of the information on how we labeled the right triangle on this unit circle. Okay, sine, opposite over hypotenuse. Well, let's look at theta. We know that the side that is opposite theta is y units, and the hypotenuse is 1 unit. Okay, so we can say that sine is y over 1, which is equal to y. Okay. Furthermore, for cosine, we see the side adjacent to theta is x, the hypotenuse is 1, so adjacent over hypotenuse is x over 1, or x. Okay, and finally, tangent is opposite over adjacent. Opposite over adjacent is y over x. Okay. So we've labeled each of these trig functions in terms of the labels that we've given to this triangle. Okay. Now we can label this even further now. Notice that cosine of theta is equal to x. Therefore, what I can do is label this coordinate, instead of labeling it xy, I can label x cosine theta, and y, as you'll notice here, is equal to sine theta. So I can say that this coordinate is cosine theta, sine theta. Furthermore, looking down here at our labels, because sine is equal to y, I can say that numerator of tangent is sine theta. And because cosine is equal to x, I can say the denominator here is cosine theta. So one way to describe the tangent is as the sine of theta over the cosine of theta. Okay? Now, one thing we can do also is, in addition to the coordinate that we've labeled here in general terms, cosine theta, sine theta, we can give specific labels to the corner coordinates. In other words, this coordinate, this coordinate, this coordinate, this coordinate. As you know, that the radius is 1 unit, and so we have an infinite number of radii going around this circle. We know here's a radius, of course, here's a radius, here's a radius, here's a radius. We all have we have also other diagonal radii here. But because this is 1 unit, I can then label this coordinate 1, 0. And this coordinate here, 0, 1. And here, -1, 0. And here, 0, -1. Okay? Now, let's look at how we can use the information here that we've already determined to find the sine, cosine, and tangent of corner angles on the unit circle. And again, the corner angles I'm talking about are at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and again, bringing back up here, 360 degrees. So we can see that x and y for any coordinate is the same as cosine theta, sine theta. Okay? So just as an example here, for 0 degrees or 360 degrees, the cosine of 0 degrees is 1, and the sine of 0 degrees is 0, right? Because for every coordinate on the circle, we have cosine theta, sine theta. And furthermore, the tangent, you can see, is sine over cosine. So I could also find the tangent here, right? So the tangent being sine over cosine would be 0 over 1 or 0. Okay, and you could verify this on your calculator. For example, if I want to check, make sure, by the way, again, we talked about this in prior sections, make sure your calculator mode is in degrees. Okay, so if I wanted to find, just to verify on my calculator, the cosine of 0, okay, so cosine of, and I'll lower the lamp here a sec, so hopefully maybe that'll help you see it a little bit better. The cosine of 0 is 1, exactly what we have here on the coordinate, right? And you can expect if I hit sine of 0, I'm going to get 0. Watch. Sine 0, 0. And tangent is sine over cosine. 0 over 1 is 0. So the tangent of 0 is going to be 0. Okay? All right, so let's look at some angles down here. So we want to find the sine, cosine, and tangent of the following angle measures. Okay, so to figure this out, the first thing that you want to do is to find the coordinate. Okay, so you need the coordinate first. If you don't know the coordinate at that angle measure, you can't find the sine, the cosine, and the tangent. So at 90 degrees, if we look back up at our circle, we see that the coordinate is 0, 1. Okay, so with the coordinate being 0, 1, it's very, very straightforward. I then label cosine theta, sine theta. Okay, and so immediately I can see that the cosine of 90 degrees is 0. The sine of 90 degrees is equal to 1. Okay, now let's check the tangent. The tangent of 90 degrees is going to equal, as you can see from up here, our formula, the sine of 90 over the cosine of 90. Okay, so the sine of 90 is 1, the cosine of 90 is 0. So think about what 1 over 0 is. And hopefully you recognize that is undefined. Okay, so to see how that, you can imagine what happens on your calculator with that, right? If I do the tangent of 90, I get error because it's undefined and we can't calculate it. You see? All right. Now, I can also, if I wanted to, calculate, for example, the reciprocal functions for any of these, okay? So, for example, let's say I wanted the cosecant of 90, okay, just as an example here. Remember, the cosecant is just the reciprocal of the sine. So cosecant of 90 would simply be 1 over 1, right? The reciprocal is 1 over whatever that value was. And so you can see the cosecant of 90 would be 1 as an example, right? Also, let's say I wanted the secant of 90. That would be, of course, 1 over 0. And just like tangent was undefined, secant of 90 would be undefined, right? But let's say I wanted the cotangent of 90, right? The cotangent of 90 would be 1 over the tangent. And so basically you just be flipping over. 1 over 0 would become 0 over 1. So the cotangent of 90 is defined, it's 0. Okay? So we've answered the question. Specifically, we were asked for what's the sine of 90, what's the cosine of 90, and what is the tangent of 90. Okay? Those 3 questions were answered. Plus, I went a little bit farther and I found the reciprocal functions too, just in case something like that comes up in the assignment, you know exactly what to do with that. Okay? Let's look at 180 degrees. Okay, think about what you have to do first to figure out what the cosine, sine, and tangent are at a specific angle. You need to know the coordinate. Okay, so you can see for 180, the coordinate is -1, 0. Okay, so at -1, 0, you've got cosine and sine. And by the way, to remember which comes first, what I like to tell students is think logically here. The reason we know cosine is the x value and sine is the y value is alphabetically cosine C comes before sine S, just like x comes before y. Okay, so hopefully that'll help you. You can even, if you want to recognize that up here as well, you can maybe highlight that and remind yourself that, you know, it's alphabetical. So put in alphabetical order. Okay? All right, so we can see cosine, sine, and so it's straightforward. Cosine 180 equals -1. Sine 180 is equal to 0. Tangent, of course, is going to be, and I'll kind of get this out of the way because it was for the prior question. Tangent of 180 is going to equal sine over cosine, right? So 0 over -1, which is equal to 0. Okay? And of course, we could do the reciprocals of this one as well. So I think most of you probably have the idea. I would say at this point, you might want to pause and go ahead and do C and D on your own before I do them and make sure you can do them on your own, because I have a feeling many of you could. Even though, just pay attention here, you can see we're going in the opposite direction. We're going to be going clockwise because we are looking at negative degrees. Okay? All right, so cosine -90. So what we would want to do then is probably go back up to the circle and label it in the opposite direction, right? So we've got 0 degrees here, rotating clockwise. Here we're at -90, -180, -270, and of course here we're at -360, okay? So -90 has a coordinate of 0, -1. Okay? And so we can see the cosine of negative 90 is going to be 0. The sine of negative 90 is going to be negative 1. Whoops, move this up a little bit. And the tangent of negative 90 is going to be sine over cosine, negative 1 over 0, and so that's going to be undefined. Okay? And what you should be starting to see here, of course, is that we're looking at coterminal angles, okay? So we understand that the results we're getting here for negative 90, of course, would be the same for positive 270, right? And other angles that would be at the same point, right? So like, for example, if I went whole negative 360 and then another negative 90, it would also be negative 450 degrees that would have, for example, the same cosine, sine, and tangent. Okay? All right, so here we have at negative 360, right? So negative 360, if we look carefully, of course, speaking of coterminal angles, is going to have the same cosine and sine and tangent as 0 degrees and 360 degrees, right? It's at the coordinate 1, 0. So if we say 1, 0, so the cosine of negative 360, and for these negative angles, you may want to put them in parentheses, just so to be clear, but you don't need to. So cosine of negative 360 is equal to 1. Sine of negative 360 is going to equal 0. And tangent of negative 360 is going to equal sine over cosine, 0 over 1, which is 0. Okay? So now we're looking at some angle measures in radians. So we'd want to go to our circle and label as radians. Okay? So if we do that, 0 degrees is the same as 0 radians, right? And then here we've got halfway across the circle, right, would be pi radians. Halfway there would be pi over 2 radians. Here's pi radians. Here's 2 pi radians. So halfway between 1 and 2 is 1.5, or 3/2 pi, or 3 pi over 2 radians, right? And so again, we are looking at 0, negative 1. Okay, now if we look closely here, here's the coordinate 0, negative 1. If we look carefully here, notice we have the exact same coordinate that we had in part C. So my answers to part C are going to be identical to my answers to part E. So I can literally say, copy answers from part C. They're the exact same coordinate, so therefore the exact same cosine, sine, and tangent. Okay? Let's look at negative 3 pi, which means we need to label the circle in the negative radians direction. Okay? So looking here, we are at 0. Halfway across would be negative pi. So this here would be negative pi over 2. Up here would be negative 3 pi over 2. And I'm trying to use all different colors because we have a lot of different labels at each point, right? And then finally, all the way around the circle would be negative 2 pi. But you see, we want negative 3 pi, which means this is involving not just one rotation in the positive, or in the clockwise direction, in the negative radian direction, not just one rotation, but we have to continue. So here's negative 2 pi. So if I go another negative pi, I'll be at negative 3 pi. So negative 3 pi is coterminal with negative pi, right? So this is also negative 3 pi here. And of course, I could keep going, right? Here would be negative 4 pi. Here would be negative 5 pi, and so on. So negative 3 pi has the coordinate negative 1, 0, right? So if we say negative 1, 0, and we look carefully at our work so far, we notice that we have the exact same coordinate as in part B, which means the cosine, sine, and tangent will be the same as we had in part B for 180 degrees. So I can copy answers from part B, okay? Okay, so for this next part, you're going to want to have the last page of your 7-1 notes available. And remember, we're in 7-3 now, so not last week, but the week before. Okay, and it looks like this. It's the page that says special right triangles, where we came up with the sine, the cosine, and tangent of angles that are in special right triangles, including 30-degree angles, 60-degree angles, and 45-degree angles, okay? Because those are going to be key acute angles on the unit circle where we're wanting to be able to find the sine, the cosine, and the tangent. Okay, so have this available. Again, pause if you need to find it before you continue. Okay? So I'm going to say here, we're going to be making a table here, but you're going to want to see the last page of your 7-1 notes to be able to create the table. Okay? So we're going to learn how to use reference angles to find the sine, cosine, or tangent of other angles on the unit circle. So we want to remember that reference angles are positive and acute angles that are formed by the terminal side of the angle theta and the x-axis, okay? In order to be able to find other angles on the unit circle, we're going to use the sine, the cosine, and the tangent of these reference angles, specifically 30, 60, and 45 degrees, okay? So I'm going to give you the steps here of how we're going to do this, okay? You're going to be drawing theta in standard position. You're going to find alpha. Remember, alpha is the name that we give to the reference angle. Okay? And in order to do this, we're going to use this table. Okay? So I've given you radian measures of angles. First thing you want to do is fill in the equivalent degree measures. Okay, now we learned in prior section how to calculate the degree measure for a given radian measure. Okay, and what we're going to do here is remember that pi over 3, if I convert that to degrees, is always going to be 60 degrees. Okay, pi over 4 is 45 degrees. Pi over 6 is 30 degrees. And one way to remember that is remember that pi radians is 180 degrees, right? 180 divided by 6 is 30. 180 divided by 4 is 45. 180 divided by 3 is 60. Okay? Now, if I go back to the last page of the 7-1 notes, I can basically take the values of cosine, sine, and tangent for each one of these degree measures and copy them into my table, okay? For example, for 60 degrees here, we have this problem here on that last page, and it gives us the cosine, the sine, and the tangent of 60 degrees, okay? This one is giving me the sine, the cosine, tangent of 30, and these two give me the sine, cosine, and tangent of 45. And the reason I'm pointing this out is I want you to remember where these came from. Remember, we came up with this by knowing the relationships in special right triangles and specifically calculating the sine, the cosine, and tangent by using those ratios within these special right triangles, okay? So for the cosine of 60, we have 1/2. The sine of 60 is the square root of 3 over 2, and the tangent of 60 is square root of 3. And remember, this is regardless of the actual lengths of the sides. The ratios are always going to come out the same, okay? For 45 degrees, both the sine and the cosine are the same. Remember, because these are isosceles right triangles, so the legs have the same length. And the tangent is 1 because, of course, tangent is sine over cosine, as we've just learned in this section 7.3. Okay? For 30 degrees, the cosine is the square root of 3 over 2. The sine is 1/2. And the tangent is the square root of 3 over 3. Okay? One thing you want to remember is what we learned before, that relationships between tangents of acute angles that are complementary, that sum to 90, remember they're reciprocals of one another. If I say 1 over the square root of 3 and I rationalize the denominator, I will get the square root of 3 over 3. Okay? Also remember that, for example, the cosine of 60 is going to be the same as the sine of 30. And the sine of 60 is the same as the cosine of 30. And this will help us in learning these. You know, if you were taking this course now in school, I'd be actually quizzing you and having you draw unit circles as a quiz. Every year I give a unit circle quiz, and you'd be labeling these values and you would learn them and memorize them. And honestly, I'd suggest you do that. I'm going to give you a pattern to look at. So hopefully you'll learn them, because when you get to your course next year, whether it be pre-calc or math analysis and trig, you're going to have to know that then, and you're going to have to memorize them then. So you might as well learn them now and not have to stress about it later. Okay? All right, so what we're going to do is now, of course, we have angles that are the reference angles for 60 degrees, and they might be in a different quadrant where cosine, sine, or tangent may not be positive anymore. And we're going to look at how, based on the quadrant you're in, the sine, the cosine, and the tangent are going to change signs. So we're going to be, after we've drawn the angle in standard position and found the reference angle, we're going to adjust the signs on the sine, cosine, and tangent for the quadrant that we're in. And we're going to learn how to do that now. Okay? So let's look at the table that I have down here. And what this is really, what we're going to be creating here is a coordinate plane. Okay? So what I want you to do is basically just extend the horizontal line here in the table to create the x-axis, okay, where the coordinate in the middle here is at the origin, and extend the vertical line here to create the y-axis. Okay? And so what we've created here are the 4 quadrants. Remember, when we number the quadrants, we number counterclockwise. We have quadrant 1. They're often numbered with Roman numerals. 1, 2, 3, and 4. Okay? Now, just let's go back to basics here. Okay? Before you were even in an algebra class at all, just going back to even like pre-algebra or even 5th, 6th grade math, okay? When you were first learning about the coordinate plane, you know that for any point x, y, that in the first quadrant, x has to be positive and y has to be positive, right? And you know, if we go to the second quadrant, same thing, right? Basically, we've got x is negative, y is positive, right? Because as you move, negative, positive, right? And then continuing here to the third quadrant, x is negative, y is negative. And moving to the fourth quadrant, x is positive and y is negative. Okay, so how does that help us in trigonometry? Well, we've just learned that the x value corresponds to cosine and the y value corresponds to sine. Okay, And we also have learned that the tangent is going to equal the sine over the cosine, right? And so in quadrant 1, sine is positive and cosine is positive, and a positive divided by a positive gives us a positive, which means that in quadrant 1, all of the trig functions, the 3 main trig functions, not the reciprocals, but if I were to do the reciprocals, they would have the same sign as the original trig functions anyway. All 3, sine, cosine, and tangent, all are positive. Okay? So I'm going to label that as such. I'm going to say all are positive. And let's see, I'll use a different color here. I have a reason for making those 2 different colors, and you'll see shortly. Okay? So all 3 trig functions are positive here. Okay? Let's look at quadrant 2. If we look at quadrant 2, you notice that the sine is positive, right? Because if you want, we can label that here too. So we know this is cosine and this is sine, right? So we can see that the sine is positive. Check out tangent. Tangent of theta is equal to sine over cosine, so positive over negative. So that's going to equal a negative. Okay? So in this particular quadrant, only the sine is positive. Okay? Okay, let's go to the third quadrant now. In the third quadrant, we've got cosine, sine. Okay, neither cosine nor sine are positive. When I go to tangent, sine over cosine and negative over negative equals a positive. So in the third quadrant, tangent is positive. Okay, and so I'm going to label that as such. I'm going to say tangent is positive. Okay, now fourth quadrant, cosine of theta, sine of theta. In the fourth quadrant here, we can see that cosine is positive. Okay, let's check out the tangent. The tangent of theta equals sine over cosine, right? So we're going to do sine over cosine. So a negative over a positive is going to equal a negative. And so we can see in the fourth quadrant, only the cosine is positive. Okay, so to kind of remind you what we're asking here, you know, what you can do is you can label this table or this set of this coordinate plane as which functions are positive. Okay, so which functions are positive in which quadrants? And so we can see basically in the first quadrant, all 3 are positive. In the second quadrant, just the sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. And rather than having to every single time have to think about it too much, we can use the letters A, S, T, C to help us. Okay, so we have, and you can see over here, I say mnemonic. Okay, so this is the mnemonic on the bottom where you've seen I've left 4 blanks. Okay, so I've got A, S, T, C. Okay, and a lot of teachers use the same mnemonic. The words we're going to put to this, which aren't actually necessarily true in practical terms, but we use it to help you remember this. is that all students take calculus. Okay, so there's the mnemonic to help you remember in which quadrants each trig function are positive. Okay, that's how we're going to be able to figure out the sine, the cosine, and tangent for every angle on the unit circle. Okay, now just as a note on the side here, before we go on, that reciprocal functions are positive and negative in the same quadrants as the originals. Okay, so for example, cosine is only positive, or basically cosine is positive in the first quadrant and in the fourth quadrant, just by itself in the fourth quadrant, and with the other two trig functions as well in the first. So that means secant is as well, because it's reciprocal. Okay, and the same goes for sine. Wherever it's positive, the cosecant is positive. Wherever the tangent is positive, the cotangent is positive. Okay? Okay, for this next section in topic 7.3, you may want to have your 7.2 notes available where you labeled the unit circle. Okay, so you may want to have this available. We're going to be labeling the unit circle again shortly, but we're going to be adding coordinates to it. Okay, so when we do that, you might want to pause and see how much you remember and see if you can remember the patterns that we learned to be able to try to label on your own, at least for the degrees and the radians, and then I'll show you the pattern in the coordinates as well. So have this page available. Okay. We're going to be looking now at what are the sine and cosine of various angles on the unit circle, and we're going to use what we just learned about reference angles and how we're going to change the signs of the sine, cosine, and tangent based on the quadrant that theta is in. Okay? So we're going to find what are the sine and cosine of the angle 2 pi over 3. Remember that if we look back at the steps, and remember when I say the steps, what I'm saying are right here. It says to draw the angle in standard position and then find the reference angle. Okay, so that's what I'm talking about here. So we want to draw 2 pi over 3 in standard position. Okay, now at this point, you might remember if you had your unit circle available where 2 pi over 3 is. Okay, it's equivalent to 120 degrees. If you didn't, then you might want to convert 2 pi over 3 to degrees because you're much more familiar at this point with degrees and you might be able to draw it more easily. Okay, and by the way, later on as you move into your next math class, radians are going to be much more basically you're going to be used to radians much more than degrees actually. Okay, so 2 pi over 3. Basically, we know that pi over 3 is equivalent to 60 degrees. So 2 pi over 3 is equivalent to 120 degrees. So we're basically at 90 degrees plus another 30. So here's theta. And that theta is 2 pi over 3. Okay. Remember, right after that in the steps, we want to figure out what alpha is. Okay, so we know that if we were to label the coordinates or the axes here based on radians, we know that here we've got 0 or 2 pi radians. Halfway around the circle, we're at pi radians. Halfway between 0 and pi radians is pi over 2. And of course, here we've got 3 pi over 2. Okay, so if you're trying to figure out what the reference angle is, remember the reference angle is based on the angle that's formed between the terminal side of the angle theta and the x-axis. Okay, so alpha is right here. So some of you intuitively might know that, well, I've gone 2/3 of the way to pi. Here's pi, I've got 1/3 of pi left. So that's pi over 3. Okay? Some of you might want to do some subtraction. For example, pi minus 2 pi over 3 will tell us what is left here for the reference angle. And if you write in terms of the same common denominator, if we put that pi over 1, the LCD here is 3. So we'd change the denominator here to 3. 1 times 3 is 3, and 3 times pi is 3 pi. 3 pi minus 2 pi over 3 gives us the pi over 3 that we found here for the reference angle. Okay? So since we know the reference angle is equal to alpha is equal to pi over 3, we are going to find the cosine, the sine, and the sine of that reference angle, and then adjust our signs given the fact that we are here in quadrant 2. Okay? And remember, if we use the mnemonic we were talking about, all students take calculus. We know that in quadrant 2, where the terminal side of this angle lies, only sine is positive. Okay, so when I find the cosine and the sine, I need to keep in mind that sine is going to be positive, but in my answer, cosine is going to be negative. So for this, our answer's positive here and negative here. And that's how we adjust the signs for the quadrant. Okay, now for the cosine of pi over 3, which is our reference angle, the cosine of pi over 3, if you look back in your table, if you don't remember it, that's 1/2. Okay? Now, for the cosine of 2 pi over 3, the cosine of 2 pi over 3 is simply going to be negative 1/2. It's going to have the same absolute value, but the sign is going to be negative. Okay, and shortly after we do this page, we're going to label the unit circle with coordinates, and you'll see exactly on that unit circle that the cosine of 2 pi over 3 is negative 1/2, and you'll understand a little bit better why that is true. So we've got the cosine of 2 pi over 3 is negative 1/2. Now if I want to do the sine of pi over 3, the sine of pi over 3 is the square root of 3 over 2, which means, again, it's going to remain positive. So we're going to say that the sine of 2 pi over 3 is going to be the square root of 3 over 2. It's going to stay positive. Okay? Now note for just reciprocal functions. We weren't asked for it specifically here, but I also just want to remind you how we would do this, just in case you were asked, right? So let's say I wanted the secant of 2 pi over 3. That's just going to be the reciprocal of negative 1/2. It'll be negative 2 over 1. So that'll be negative 2. Okay, and the cosecant of 2 pi over 3 is going to be the reciprocal of the square root of 3 over 2. So it's going to be 2 over the square root of 3, but the only thing is we're going to want to rationalize the denominator, so I'll multiply the numerator and denominator by the square root of 3. So the numerator will be 2 square root of 3. The denominator will be square root of 3 times square root of 3, which is just 3. Okay? Let's look at the sine and cosine of an angle in degrees, 225 degrees. Okay? Now, if we label the axes here, 0 degrees, which is also 360, 90, 180, 270, hopefully we recognize here if we're going to be rotating counterclockwise, because this is a positive angle measure, 225 is going to be between 180 and 270. Okay? And if you're not sure exactly where, okay, you can look at the difference between 225 and 180. So we could say 225 minus 180 is 45 degrees, which means when we rotate around the circle, we'll rotate 180 and another 45 degrees will land us at theta equals 225 degrees. But interestingly enough, that also helps us out because now we can actually see that, remember, the reference angle is formed by the terminal side of the angle in the x-axis. So we can see also that alpha has to be 45 degrees, okay? Okay, so before we calculate sine and cosine, we want to look at the quadrant again. We see that all students take calculus. So here in quadrant 3, only the tangent is positive, which means that both the sine and the cosine are going to be negative. So we want to make sure to put negative signs on our answers, okay? So for the sine of 45 degrees, we know that that's the square root of 2 over 2. And by the way, the cosine we know of 45 degrees is going to be the same, square root of 2 over 2. If we use that reference angle to figure out the sine and cosine of 225, we know that we are simply going to take the same absolute value but put negative signs. So negative square root of 2 over 2 and negative square root of 2 over 2. Okay? And of course, for the reciprocal functions here, again, I didn't ask that specifically here. Make sure for your reciprocal functions, make sure you'd understand that what you would do is you just flip those over and just make sure when you do that to rationalize the denominator. Okay? I'm not going to do those again here. You got the idea up here. Okay? All right, so we're going to now use reference angles in the unit circle to evaluate tangents. We're going to figure out the tangent of the angle negative 5 pi over 6. So what I want to do is I'm going to want to label my axes with negative radians, right? So I have 0, and this is also negative 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, okay? So hopefully, if you recognize we're rotating clockwise here, negative 5 pi over 6 is negative 5/6 of the way to pi, right? 5/6 of the way across the circle, right? So you basically have 1/6 of pi left here. So already, just by saying that, with 1/6 of pi left, hopefully you realize that alpha is pi over 6. Okay, keep in mind, remember, reference angles are always acute and positive. So even though this was a negative 5 pi over 6, I'm going to say alpha is pi over 6. Another thing to remember is, remember we learned in 7.2 that when you're dealing with denominators of 4 and 3 and 6, when you're looking for the reference angle, it can be found just by looking at the actual fraction and taking off that coefficient, okay? So the reference angle here, alpha, is equal to pi over 6. And of course, theta here was negative 5 pi over 6, okay? There's alpha, okay? So if I want to find the tangent of negative 5 pi over 6, remember, let's label our quadrants appropriately so we know that all students take calculus, okay? So we here are in the third quadrant, just like we were in example 2b up here. So only tangent is positive, which means that our answer will remain positive. So whatever the tangent is for pi over 6 is going to be the tangent with the same sign for negative 5 pi over 6, okay? So we know that the tangent of pi over 6, if you look back at the table that we made, we've got the square root of 3 over 3, which means that the tangent of negative 5 pi over 6 is going to be exactly the same square root of 3 over 3. Okay? And just to do, reciprocals here for a moment, just because we did it up here with sine and cosine once, I'll do the same down here one time. So for the reciprocal function, the cotangent of pi over 6, whoops, I meant to write cotangent and not cosine there. So let me just change that s to a t. So the cotangent of negative 5 pi over 6 is just going to be the reciprocal, right? So it's going to be 3 over the square root of 3, and just rationalize that denominator, square root of 3 over square root of 3, which is going to be 3 square root of 3 over 3, which if we cancel just gives us the square root of 3. Okay? Something to notice here is remember that tangent and cotangent are reciprocals of one another, but also remember if we look back at our table, see we have here the tangent of pi over 6, the square root of 3 over 3, but look at the tangent of pi over 3. It's the square root of 3, which is the same as the cotangent of pi over 6. You see, the tangent and the cotangent are reciprocals, but remember we learned also, if you go back to section 7.1, the first page, remember that if you have angles that are complementary, like here alpha and beta, their tangents are going to be reciprocals. So pi over 3, pi over 6, 60 and 30, they're complementary, so their tangents are reciprocals. Okay, so these are relationships to know, to think of this, in a higher level. All right, finally here on this page, the tangent of the angle 7 pi over 4. Okay, so again, I should be able to immediately recognize that the reference angle is pi over 4. That I get just by looking at the fraction. Okay, but I want to be able to draw this in the correct quadrant so I know whether 7 pi over 4 is going to be positive or negative, right? So I'll label the quadrants 0, pi over 2, pi, 3 pi over 2, and 2 pi, okay? And recognize if we're saying theta equals 7 pi over 4, think about that, right? So 7/4 is less than 2, right? 8/4 is 2. So even though this is an improper fraction, don't get confused and think you're going more than one rotation around the circle. We're actually going a little bit less than one rotation around the circle, right? If we recognize here, for example, 3 pi over 2 here is 1, 2, 3/4 of the way around the circle. And 7 pi over 4, if we were to count in terms of fourths here, we've got 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. Okay, so 7/4 pi is just going to be basically 1/4 of the way less than one full rotation around the circle. And so you can see here alpha is going to equal pi over 4. Theta is going to be 7 pi over 4. Okay, and again, you'll see this again in a moment when we review the labels on the unit circle. Okay, so remember, we have again, all students take calculus. Okay, so here's the terminal side of the angle right here. It's in the fourth quadrant. And we can see in the fourth quadrant, only the cosine is positive, which tells us that our answer for tangent here is going to be negative. Okay? So the tangent of pi over 4 is equal to 1, but because we're in the fourth quadrant where tangent is negative, the tangent of 7 pi over 4 is going to equal negative 1. Okay? So we're going to go on now And again, you may want to pause to just absorb what we just did. We're going to go on and we're going to label the unit circle just like we did in section 7.2, only this time we're going to add on coordinates based on what we've learned about how sine, cosine, and tangent are found by looking at the coordinates on the unit circle. Okay, so you may want to pause here and see if you can remember how to label the coordinates in terms of degrees and radians, or label the points on the unit circle, I should say, in terms of degrees and radians. Then we're going to go on and we're going to label using the coordinates as well. Okay, so remember here that at the center here of the unit circle, we are at the origin at 0, 0. Okay, remember, given that this is a unit circle, each one of these line segments here represents a radius, right? I could keep going around the circle. All of those radii would be equal to 1, radius equal to 1, radius equal to 1, and so on. I could keep going all the way around, right? So as far as coordinates here, we have 1, 0, 0, 1, negative 1, 0, 0, negative 1, right? Okay. So before we label other coordinates, let's go back and just see if we can remember how to label in terms of degrees. Okay, so we have 0 degrees here, or 0 radians, also 360 degrees. Okay, here we have 90 degrees. Here we have 180 degrees. Here is 270 degrees. Okay. Then remember what we did is we labeled the 45 degrees, right? So we have, I guess I'll use the same color for those. 45 plus 45 is 90, plus 45 is 135, plus 45 is 180, plus 45 is 225, plus 45 is 270, plus 45 is 315, plus 45 is 360, okay? Now I will label the multiples of 60 degrees, okay? So we've got 60 degrees here. 60 and 60 make 120. 120 and 60 make 180. Plus 60 make 240. Plus 60 is 300. Plus 60 is 360, okay? Next, we'll do multiples of 30 degrees. We've got 30 degrees, plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, plus 30, 180, plus 30, 210, 210 and 30, 240, 240 and 30, 270, plus 30 is 300, plus 30 is 330. Okay. Now, before we continue here, hopefully this will help you see what we were talking about here in terms of reference angles. You see, if you look, for example, at 30 degrees, it's basically in the same position in quadrant 1 that 150 degrees is in quadrant 2. So whatever the coordinates are of the 30-degree angle here are going to be the same as the coordinates of the 150-degree angle, only the 150-degree angle is going to have x negative instead of positive, okay? And that's why you can see there's a pattern here. All right, so let's look now at the radian measures, okay? So we know we've got 0 radians and also 2 pi, okay? At 90 degrees, we have pi over 2. At 180 degrees, we have pi. At 270 degrees, we have 3 pi over 2. And at 360 degrees, we have 2 pi, okay? Now we know half of a half is a fourth, so at 45 degrees, we have pi over 4. Okay, so let's start counting and adding on fourths. So we have 1/4 and 1/4 is 1/2, and 1/4 is 3/4. So here we're at 3/4 pi, or 3 pi over 4. Add another fourth, we're at 4/4 pi, or pi. Another fourth, we're at 5/4 pi. Another fourth, we're at 6/4, or 3 pi over 2. Another fourth, we're at 7 pi over 4. And then finally, 8 pi over 4 is 2 pi. Okay? Let's look in terms of 60 degrees. Remember, 60 degrees is 1/3 of the way to pi. So we have 1/3 pi. Add another third of pi, we'll land at 120 degrees, so that's 2 pi over 3. Add another third, we'll be at 3 pi over 3, or pi. Add another third, or 60 degrees, we'll be at 4 pi over 3, 4/3 pi. Another third will be at 5/3 pi. And finally, 2 pi is 6/3 pi. Okay? Now let's start at pi over 6 and add on 6. 1/6 and 1/6 is 2/6, but that's 1/3. We've already got it. Okay? So another 3/6 is 1/2. That's we've already got. 4/6 is 2/3. We already have that. Then comes 5/6. So that's 5 pi over 6. 6/6. 7/6. 7 pi over 6. Okay? 8/6 is 4/3. 9/6 is 3/2. Okay? 10/6, 5/3. 11/6, 11 pi over 6. 12/6, 2 pi. Okay? Now this we all did before. We labeled the same thing in section 7.2. And again, I want to remind you that had we been learning in the classroom, it would be different. And we would definitely have you memorize this. Normally every year I have students make a paper plate and learn the coordinates and the degrees and the radians around the unit circle. And on a quiz, basically you get a quiz that looks identical to this and you fill everything in. So to test yourself, what you might want to do is just print several copies of this page, whether it be, this page is available in the 7.2 document or the 7.3 document, either one. And if you print several copies of this page, if you have time, it's a really good idea to prepare you for your next math class, because you will be asked to learn it from memory there. Okay? All right, so we're going to go on now and we're going to look at the coordinates in terms of sine and cosine. So you want to remember what we just learned, that basically for every coordinate x, y on the circle, we have cosine of theta and we have sine of theta. Okay? And so I'm going to label the coordinates around the circle, and you want to keep that in mind. And remember, it's always easy to find tangent, because the tangent of theta is going to be the sine over the cosine. Okay, so we're going to label the coordinates here. And of course, I'm getting the same values that were in the table. So if you remember just a couple pages back, we have the values for 30, 45, and 60 right here in the table. But I want to show you how you can help learn it. Okay? First of all, we already have labeled the coordinates for the corner angles. That's already done. So like, for example, here, we already know the cosine of 0 degrees or 0 radians is 1. The sine of 0 degrees or 0 radians is 0, right? But if we go to each one of the acute angles, we can do the same thing, okay? And so I want to show you the pattern. This is how you remember it, okay? So let's just make the parentheses and the commas for the coordinates, and let's just fill those in, okay? So watch carefully, and you may want to rewind or pause to follow the pattern that I'm showing you here, okay? So this is what you're going to do. You might want to stop and watch and then pause and fill it in. So this is how we're going to look at the pattern. We're going to go from top to bottom, and we're going to say 1, 2, 3, 1, 2, 3. Put them all over 2 and take the square root of the numerator. Okay, now when I take the square root of the numerator, keep in mind the square root of 1 is 1, so I'm not going to put a square root symbol on that. So the square root of 3, the square root of 2, the square root of 2, the square root of 3, and of course square root of 1 is 1. So you see the pattern again. 1, 2, 3, 1, 2, 3, put them all over 2 and take the square root of the numerator. Okay? This pattern is going to be preserved from quadrant to quadrant, keeping in mind the all students take calculus. All students take calculus, right? So in the second quadrant here, you can use the color coding that I gave you here. See these same coordinates? You're going to have them in the same spot, only of course in quadrant 2, only sine is positive, so the x value is going to be negative. And logic would tell you this anyway, right? Because look, negative, positive, just going back even years ago, you know this about a coordinate plane. Okay, so what I can do if I want to fill in the second quadrant here, I can do the same thing. Okay, I can basically put place for my coordinates here. Okay, and I can fill them in, keeping in mind that again, in all cases here, the x value is going to be negative because in the second quadrant, cosine is negative. After I've labeled the x value negative, I can copy everything else the same. I can say 1, 2, 3, 1, 2, 3, put them all over 2. And take the square root of the numerator. Okay, so be careful when you take the square root, don't put the negative inside the square root. Okay, so of course then it'd be an imaginary number, right? We're not taking the square root of the negative. So that'll give us, you can see for example here, see for 2 pi over 3, cosine's negative 1/2, sine square root of 3 over 2. Let's look back at our answers here. We had to find the sine and the cosine of 2 pi over 3. Cosine negative 1/2, sine square root of 3 over 2. So this kind of helps you see that we learned how to find sine, cosine, tangent using reference angles, okay? But also, if you learn the unit circle, then it's very simple to know the cosine and the sine for any angle on the unit circle, okay? Now, to do the angles that are below the x-axis, you're going to need to reverse the order here, okay? Because notice, green goes with green, purple goes with purple, blue goes with blue, right? Or if you look at the denominators, the denominator of the 3 has to go with the denominator of a 3, denominator of 4 goes with denominator of 4, denominator 6 goes with denominator 6, okay? So when you're filling in the coordinates here, you want to be mindful of the signs, and you want to be mindful of that. It's basically a mirror image here. Think of the x-axis as a mirror. So you've got a mirror image here of what you have in the numerator. Just adjust for the signs. Keeping in mind that only cosine is positive in the fourth quadrant. So you want to make sure that the y value, which is the sine, is negative. So put that negative sign on there. Then since we went 1, 2, 3, we went 1, 2, 3, 1, 2, 3 up here. Down here, we're going to say 3, 2, 1, 3, 2, 1. Put them all over 2. Them all over 2 and take the square root of the numerator. keeping in mind not to put that negative sign in the square root. And actually I put an extra square root here that it doesn't really matter. The square root of 1 is the same as 1, but that's just a 1. Okay, and also this 2 came out looking a little bit funky, so I'll make sure that we all see that that's a 2. Okay, all right. Finally, let's look here at the third quadrant. Now, the third quadrant, again, keep being mindful of the signs here, right? Only tangent is positive, which means x is negative, y is negative, cosine's negative, and sine is negative. So when you're putting your coordinates here, make sure you put negative signs on both x and y, okay? Okay, so we're going to make sure to put negative signs on x and y. And again, we got the mirror image of above the x-axis. So your order is the same as what you did here in quadrant 4. 3, 2, 1, 3, 2, 1. 3, 2, 1, 3, 2, 1. Put them all over 2. And take the square root of the numerator, not putting the negative sign inside the square root. Okay? And so now you can see what I've done is I've filled in the entire unit circle. Okay? The entire unit circle here is filled in, including degrees, radians, and coordinates. Okay, so before you go on, make sure that your unit circle looks identical to mine and that you've made no errors as far as signs or numbers, anything. Because if you learn from wrong notes, it's going to be difficult to unlearn it. So make sure you have exactly what I have if you need to pause it. Okay? All right, so let's look at example 4 here. We're going to use here what is called the Pythagorean identity. And also, in the process of this page also, we're going to use the same type of principle we used in section 7.1, if you have that available as well, where we use one trig ratio to find other trig ratios, and where we use the Pythagorean theorem to do that. We'll also be able to apply that here. Okay? So we're going to learn what's called the Pythagorean identity, and it is sine squared plus cosine squared equals 1. When you go to pre-calculus or trig next year, you'll be learning other trigonometric identities as well. Okay, so first of all, we're going to use one of these circles here to help us to understand where this trig identity comes from. Okay, so let's just, on this circle here, let's do exactly what we did earlier. Well, let's draw a radius of 1 as the hypotenuse of a right triangle. Okay, and where we have one leg representing the x distance and the other leg representing the y distance. And of course, then we have a coordinate here, x, comma, y. Okay? So we know the Pythagorean theorem applies to any right triangle. So if we look at the Pythagorean theorem here, using what we see here, we know the Pythagorean theorem tells us that x squared plus y squared equals 1. However, we're also, or I could even say this, x squared plus y squared equals 1 squared, okay? So then, of course, what that simplifies to, because 1 squared is 1, x squared plus y squared equals 1. Now, we know from this section that the x value is going to be the cosine of theta, and the y value is going to be the sine of theta, right? And so if just doing some simple substitution here, that gives us the Pythagorean identity. Cosine squared of theta plus sine squared theta equals 1. Okay, because cosine is x and sine is y. Now, of course, normally it's written in the opposite order. This is cosine first, then sine, but of course, addition's commutative. The order we write it in doesn't matter. That's how we came up with sine squared plus cosine squared equals 1. Okay, so how is this going to help us here? Well, it says here, what is the sine of theta if the cosine of theta equals -3/5 and the angle with measure theta is in quadrant 3? Okay, so we know here's quadrant 1, here's quadrant 2, here's quadrant 3, here's quadrant 4, and we know that all students take calculus. So in quadrant 3, we know that only the tangent is positive, right? Which means, since we know that theta is going to have its terminal side in quadrant 3, not only is the cosine going to be negative, we know that the sine is going to be negative. Okay, so how is that going to help us here? Well, let's apply sine squared theta plus cosine squared theta equals 1 as a formula and substitute in the cosine of theta is -3/5 and see if we can find the sine of theta and solve for it. So sine squared theta plus cosine squared theta. Well, cosine of theta is -3/5. So we'll just say, we'll square that, equals 1. Okay, so we have sine squared theta plus 9/25 equals 1. And to solve for sine squared, I'm going to need to subtract and then take the square root, right? So thinking about this logically, if I subtract 9/25, remember that, going back to basics here, 1 is the same as 25/25, right? So we've got 25/25 minus 9/25. So that means that sine squared theta is 25 minus 9, or 16/25, right? Now, if I take the square root, sine of theta, remember we do plus or minus here, is going to be plus or minus 4/5. Now, all we need to do is just adjust for the third quadrant. Because we're in quadrant 3, we just saw that sine has to be negative, so we know that sine of theta is going to be -4/5. And that would be the answer to the question. Okay? So that gives us one method to be able to do this. Okay? Let's look at an alternative method, very, very similar to what we did when you were in section 7.1, example 2. Okay? In section 7.1, example 2, which I pulled out here, you're given a trig function and you labeled the information on a right triangle in order to find the other trig function. So you might want to pause and take a look at that for a moment if you like, and then continue. Okay? All right, so what I'm going to do is I'm going to see that the cosine of theta is -3/5 and the terminal side of the angle is in quadrant 3. Okay, so I don't have to worry about drawing to scale here or anything. What I know is I've got theta here, and I don't know what theta is. I'm not concerned about the exact measurement of theta. I just know that its cosine is -3/5. Okay, so let's just ignore the sign for a minute because we know that lengths have no sign to them. They're neither positive nor negative. And let's just complete a right triangle here. Okay, and again, don't worry about this being to scale or not. Remember, cosine is equal to 3/5 if we ignore the signs, given we're talking about lengths, which is adjacent over hypotenuse. So if here's theta, let's call the angle that is within this right triangle here, formed by the terminal side of the angle and the x-axis, let's call that alpha. Okay? So if we look at alpha, we know that the adjacent side is going to be 3 units and the hypotenuse is going to be 5 units. Okay? Now I could use the Pythagorean theorem here, but most of us are familiar with, especially from geometry, that a Pythagorean triple exists that tells us if one leg is 3 and the hypotenuse is 5, that the other leg is 4. Okay? So now from that, I can see that opposite over hypotenuse is sine, which is 4/5. And all I need to do then is adjust it for the third quadrant where sine is negative. So this part is optional. It's an alternative method to using the Pythagorean identity. Many students prefer to just draw the picture, and then all of this becomes unnecessary. Okay? So I'm going to do the same here with part B. Okay? So if we look at part B here, I will use the Pythagorean identity and then show you how, if you drew it, if you wanted to, you could do it using Pythagorean theorem instead. Okay? So looking at the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. Here we're looking, we say, what is the cosine of theta is what we're looking for. So sine is going to be the square root of 2/2, and that's squared. We're looking for the cosine. You notice how this is worded a little differently. It says the angle, which means the terminal side of the angle, is in the interval between 0 and pi/2. Okay? So here you probably want to label 0, pi/2. Okay? So the interval between 0 and pi/2 is right here. So the terminal side of the angle is going to intersect somewhere along this arc in the quadrant 1. Okay, so this is really saying that we're in quadrant 1. Okay. In other words, here is the angle. Okay. And theta then is actually equal to alpha because we're in quadrant 1. All right, so what I'm going to do is recognize that in quadrant 1, all trig functions are positive. So my answer here is going to be positive. Cosine is going to be positive. Now, when I square, remember squaring the numerator, square root of 2 squared is just going to be 2. 2 squared is 4. Right? Plus cosine squared theta equals 1. So of course 2/4 is the same as 1/2. So I'm subtracting 1 minus 1/2 gives me 1/2. So I'm saying that cosine squared of theta equals 1/2. Then just take the square root of both sides. Okay? Cosine of theta is equal to plus or minus. The square root of 1 is just 1 over the square root of 2. Okay? So make sure you rationalize the denominator. So you're going to get plus or minus 1 times the square root of 2 is square root of 2. Square root of 2 times square root of 2 is just 2. So cosine of theta is going to be plus or minus the square root of 2/2. And so hopefully you recognize what degree measure or radian measure that is at this point, right? We know that the cosine is square root of 2/2 at pi/4 or 45 degrees. Okay, and we weren't asked that in this question, but hopefully you recognize that. Okay, now because we're in quadrant 1, we need to recognize we're positive, so the cosine of theta is simply going to be the positive value. Whoops, that's just a 2, not a square root of 2 in the denominator. So that's just going to be the cosine of theta is going to be the square root of 2/2. Okay? And you might be perfectly happy leaving it at that and not worrying about the alternate way to do this. But the alternate way to do this that many people prefer, okay, is to recognize, right, sine is square root of 2 over 2. So if sine of theta is equal to the square root of 2 over 2, that's opposite over hypotenuse, right? So the hypotenuse is 2, opposite is square root of 2, okay? And you can do the Pythagorean theorem to figure out that x is also, the x distance here is also going to be the square root of 2, right? And if you're not sure, and you might even recognize that 45 degree relationship to recognize that the x value is going to be the square root of 2. But, you know, the other way to do it is you could use the Pythagorean theorem, right? To figure it out. You could say, call this x, and you could say x squared plus the square root of 2 squared is equal to 2 squared, right? So x squared plus 2 is going to equal 4. X squared is going to then equal 4 minus 2, which is 2. So x is equal to plus or minus the square root of 2, right? And of course, distance is only positive, so that's the square root of 2. And so doing adjacent over hypotenuse, that's where we get the cosine is the square root of 2 over 2. So again, you have a choice of either using the Pythagorean identity or drawing a picture and then either recognizing that isosceles triangle relationship, isosceles right triangle 45 degree relationship, or using the Pythagorean theorem. Okay? Okay, last one here. We're going to look at what is the tangent of theta if the sine is negative 8/10 and theta is in quadrant 4. Okay, so in quadrant 4, we've got 1, 2, 3, 4. And we know that in quadrant 4, all students take calculus. Only the cosine is going to be positive, which means that we know that this answer is going to be negative. Okay, so we do sine squared plus cosine squared equals 1. Sine is negative 8/10. Cosine squared is what we're going to solve for. So you notice here we're going to want tangent. You see, in the end, what we're going to have to do when we're done is we're going to have to say tangent of theta equals sine over cosine to be able to get the tangent, because within this formula we don't have tangent. So we're going to solve for cosine, then use the sine and the cosine to get the tangent. That's the plan. Okay? So squaring negative 8/10, 8 squared is 64, so negative 8/10 squared is 0.64, plus cosine squared theta equals 1. 1 minus 0.64 is going to be 0.36, is cosine squared theta. And taking the square root, the cosine of theta is going to equal plus or minus 0.6. Now, of course, in quadrant 4, cosine is positive, so the cosine of theta is just going to be positive because we're in quadrant 4. It's going to be 0.6. Okay? So if I do some substitution here, sine of theta is negative 0.8. Cosine theta is 0.6. And if I simplify that, if I divide that out of my calculator, many of you might be able to see that 8 over 6 is 4 over 3. So this is negative 4/3. So you basically could say that this equals negative 4/3 or negative 1.3 repeating. I think most of you probably would just use your calculator and get the decimal value. Okay? But that's the same as negative 4/3, either one. Okay? Now, how can I do this? Some of you might say, well, how am I going to do this? This is a decimal. How am I going to do the labeling of the triangle here? You can still very, very easily do it, okay? Because think about it this way. If we look at this, we've got the sine of theta equals negative 8/10. Simplify that to negative 4/5, okay? Then look what you end up with again. Remember, sine is opposite over hypotenuse, right? So here's your theta. here's your alpha, right? So if we're, in terms of this alpha, opposite over hypotenuse, we've got 4 over 5. Again, I'm not going to use the negative because these are lengths here. So again, we have a Pythagorean triple of 3, 4, 5, right? So we know that the adjacent side is 3, correct? And so if we're looking for the cosine here, the cosine is the adjacent over the hypotenuse, which is 3/5 or the same as 6/10. So we can see it works out the same either method. And what we are specifically looking for is the tangent, which is the opposite over the adjacent, right? So the tangent is opposite over adjacent, which is 4 over 3. But of course, in quadrant 4, it's negative because only cosine's positive. Okay? That will do it for section 7.3. Make sure you review, go back if you need to, especially, taking possibly a second copy or third copy of the unit circle page and trying to fill it in. Okay? Have a great day.